All right. Good evening, good morning, good afternoon, good night, depending on when you're watching this video. In this video, we're going to work through exercise number 2 from lecture set 8, and that's on slide 19 of lecture set number 8. All right, so this is an example of conducting a statistical hypothesis test. The statistical hypothesis test can be performed in 6 steps. That's how I typically demonstrate it. And the testing procedure starts with an assumption check that is actually exactly the same as the assumption check that we had for the confidence interval procedures that we studied earlier. In this question, we have the following situation. Suppose that student debt for all second-year university students is normally distributed with mu equals $1,700 and sigma equals $330. If a SRS, so simple random sample, of 15 students had an average debt of $1,600, is there sufficient evidence to conclude that the average debt for all second-year students is less than $1,700 at the 10% significance level? So this is a fairly standard hypothesis testing scenario. In every hypothesis test or confidence interval or inferential procedure that we study in this course, we always start off by checking the assumptions. So here, we have the following. So first, SRS. This is clearly true because we're told in the problem description that we're working with an SRS. Okay, the second one is that, or the way I write it, is that we can assume that X bar is at least approximately normal. And this again is fine because we are told that student debt is normally distributed. So the variable we are studying is normal. And then our third assumption is sigma known. All right, and this again is fine because we are told what sigma is. So all this means, the first two assumptions essentially allow us to conclude that we are using a representative sample and that our test statistic, so the value that we compute on step 3, will be normal, which means that when we look for evidence, we're looking in the right place. The fact that the third assumption, so the fact that we can say that sigma is known, just means that the test statistic is going to be a z-score. So with confidence intervals, when sigma was known, we used a z value. With hypothesis testing, that's the same idea. Okay, on step 1, we declare our null and alternative hypothesis. Okay, so our null hypothesis is given by H0. All right, this question says, is there, I'll use red again, is there sufficient evidence to conclude that the average debt for all second-year students is less than $1,700? All right, so this portion of the problem description is telling us how we want to phrase our alternative hypothesis. When we teach the null hypothesis at this level, we always use an equality sign. So right now, our null hypothesis is that the mean student debt for all second-year students is $1,700. So H naught mu equals 17. In the alternative hypothesis, we declare what we're interested in checking, which is whether or not there is evidence that the mean is less than 1,700. Because again, if we review the problem, it says here, sufficient evidence, average debt, second-year students is less than 17. So this is telling us how we should set up the alternative hypothesis. So we have an alternative hypothesis of mu less than 1,700. In all situations, we will simply write the null hypothesis as mu equal to whatever the hypothesized value is. All right, step 2, we simply declare the significance level. In this problem, we want to test at the 10% significance level. Okay, so we just write here alpha equals 0.1. So we're just stating the percentage significance level in decimal form. All right, on step 3, we compute our test statistic. So we have Z. We know it's a Z score because sigma is known, is equal to X bar minus mu 0 divided by sigma over the square root of n. Okay, X bar is given to us in the problem. It's $1,600. Mu 0 is the value that we are testing, or the value that we assume mu to be equal to. In this problem, we have H0 mu equals 1700. So we take the value from the null hypothesis and we plug that in for mu naught, or mu 0. Okay. And then we divide by 330 over the square root of 15. All right, if we work this out, we get negative 1.17. I'm only keeping 2 decimal places for the test statistic because it's a Z score. So when we go to our standard normal table, which we're going to do on step 4, those are only 2 decimal place numbers. So we only need to keep 2 decimal places unless the third spot is a 5. Okay. On step 4, we can take either the critical value or the p-value approach. I will demonstrate both approaches, but you don't have to use both. So if the question doesn't state which approach to take, you can choose between the critical value and the p-value approach. If the question tells you which approach to take, then you would take that. But in no situation would you have to use both. The results will agree. So this is 2 ways of doing the exact same thing. All right, so with the critical value approach, I start by sketching a standard normal curve. Okay, so the same thing that we've been doing for a few weeks now. All right, so here's my standard normal curve. It looks something like this. Right, and this thing is centered at 0. Okay, now what I do is I take my test statistic value, which is negative 1.17, and I just mark down where this can sit on the axis. Okay, so in this case, it sits at, sorry, this is the p-value approach. Okay, so sorry about that. So I have my standard normal curve centered at 0. Now what I do is I mark down where my rejection region is located, because this is critical value. Okay, the alternative hypothesis for this test is mu less than 1700. So the symbol in the alternative hypothesis, this symbol here, the less than symbol, that tells you where the rejection region is. So our rejection region is on the left side of the curve. It's in the lower tail because it's a lower tail test. Okay, so I mark down a point and then I shade in this area. Okay, so this area here is a size of alpha equals 0.1. All right, so what we have to do next is find the Z score that makes this true. So this is going to be negative Z 0.1. All right. So to do this, the easiest way to do this, because it's a lower tail test, is go to the standard normal table and just look up 0.1 directly. All right, so if I pull up a standard normal table, which is right here, right? I'm going to look up 0.1. Right, so the closest I can get to 0.1 is 0.1003. Now I come out to my axes and I have negative 1.208. So this value here is negative 1.28, not 1.208, negative 1.28. So this number, the negative 1.28, this is the critical value. Okay. All right, so now that we have the critical value, what we can do next is mark down where the test statistic value is located compared to the critical value. All right, so if we take our test statistic, which is negative 1.7, and we mark that down on the plot. So that's going to be, for example, here, okay? So this value here is Z equals negative 1.17. Right? Now you can see that this value is not in the rejection region, right? It's outside the rejection region. So this would mean that we do not reject the null. And I'll come back to that point on step 5, because in step 5, we summarize our decision. Okay, if I take the p-value approach, I start in the same way that I do for the critical value approach. So I sketch out a standard normal curve, right? So something that looks like this maybe. I mark down where 0 is located, and now I mark down the test statistic. So let's say the test statistic is right about here. Okay. All right, and then because it's a lower tail test, I shade the area to the left of this value. So I'm going to shade the area here. Okay. And this is because of the alternative hypothesis. So the alternative hypothesis tells us where the test statistic is, or where the rejection region is located, and where the p-value is located, right? So the p-value for this test is the probability that Z is less than negative 1.17. So this green shaded part here, that is the p-value. Okay, so now I'm just phrasing it in terms of my Z score, or the test statistic. Okay, so I want the probability that Z is less than negative 1.17. So I go back to my standard normal table. I look up negative 1.107. I match those values together, and I have 0.1210. So my p-value for this test is 0.1210. All right, now on step 5, I make a decision about H0. So if I take the critical value approach, what I would say here is, since the test statistic is not in the rejection region, do not reject H0. Okay, so my decision based off the critical value is to not reject. And that is simply because the test statistic did not get into the rejection region, right? With the p-value approach, I would say, since the p-value is greater than alpha, right? So in this case, I have 0.1210 is bigger than 0.1. Do not reject H0. And as I said before, this is the same conclusion, which is to be expected. The critical value approach and the p-value approach will always agree. So you don't have to do both. It's just two different ways to accomplish the goal, which is to make a decision about H0. All right, so now I would say at the 10% significance level, the data do not provide sufficient evidence to suggest that average debt for second year university students is less than $1,700. So on step 6, we're just summarizing the result of the test in the context of the problem. So we did not reject the null, which means that we have no evidence to suggest that the alternative is actually true. So I'm just describing what that means. I start off by saying at the 10% significance level, so I declare my significance level. And then what I do is I formulate what we have determined based off the data. So in this case, I'm saying the data do not provide sufficient evidence to suggest that the average debt for second-year students is less than 1,700, right? So more simply, the data do not give evidence that the alternative could be true, but in the context of the problem. All right, so that's a statistical hypothesis test using the standard normal distribution. As always, if you have any other questions, please let me know.